Hello everyone, welcome to Lesson 1.2, Applications of Prime Factors. So today we're looking at greatest common factors and lowest common multiples. You might remember that the greatest common factor, or GCF, is of a set of whole numbers, is the largest whole number which divides into each number of the set. For smaller numbers you can usually determine the GCF through inspection or mental math. For larger numbers we need to use prime factorization. So let's do some mental math here and determine the greatest common factor of 15, 25, and 35. And I can tell that's going to be the number 5. 5 is a factor of all three of those numbers, and it's the largest one. If I look at 18 and 20, I'm thinking 2 is probably going to be the greatest common factor because 4 does not go into 18 and 6 does not go into 20. Now, example number 2, we're going to do the same thing. We're going to find the GCF of the following numbers, but this time we're going to use prime factorization. Alright, let's blow this up a little bit. We'll need some room here. So how do we do this? Well, first we have to determine the prime factors of 36 and 54. And to do that, we're going to use, I myself prefer the factor tree. So I will do that. You can use a division table if you like. So 36, I'm going to make my pen a little bit wider. 36 factors into 6 and 6, and both of those factor into 2 and 3. Oops, 2 and 3, and 2 and 3. Once I get my prime factors, I will circle them. Now, after this, I will list them all out at the bottom here in order from lowest to greatest. So 2 times 2 times 3 times 3. And that is 36 equals. Okay, 54, let me do that one in blue. 54, I'll do it up here. Factors into 6 and 9. The 6 is, again, 2 times 3, and the 9 factors into 3 times 3. And I will circle all of those as they are prime numbers. Once I get those numbers, I will list them underneath over here. So 54 equals 2 times 3 times 3 times 3. Now, how is this useful, and how are we going to determine the greatest common factor of 36 and 54? Well, we look at both of the list of factors, and we look to see which ones are common. Well, I see a 2 here and a 2 here, so both of those are common, so I'm going to circle those over here. Now I see a 2 over here, but no 2's on the bottom, so that one is not common, so I'm not going to take that one. I'll cross it out. The next number I look at is a 3, and there's a 3 here and a 3 here, so I'll take those. And then I see another pair of 3's, and then there's another 3 that's hanging out by itself here. The 36 does not have a 3, so I cannot take that one. It's not common. Once I get all my pairs, to get the greatest common factor, I just take each pair. So there's a 2 over here, so 2 times, there's a 3 over here times 3. It gives us 18. And 18 will be the greatest common factor of 36 and 54. Now you probably could have done that one in your head, but the numbers will get bigger and bigger, and we will have to use this technique to determine the GCF and the lowest common multiple a little bit later. Okay, moving on. I will like you folks to try B, and C at home, and I will jump on to D over here. Alright, let me again zoom in a little bit. There we go. Okay, so my numbers now are a little bit bigger, and I probably cannot do the GCF of 154 and 198 in my head, so I need to do the prime factorization method. So I'll start with a tree again. So 154, I'm not really sure where to start here, but I know 2 will work for sure because it's an even number. So 154 divided by 2 gives me 77, and 2 is a prime number, so I'll circle it. And the 77 further splits into a 7 and a 11, and that's it because both of those are prime. So once I determine that, I'm going to list them at the bottom here. So 154 equals 2 times 7 times 11. Do this in order from the least number to the greatest number. It'll be easier for you to determine the greatest common factor. Okay, 198. I'll do that one over here. 198 factors into 299. The 2 is a prime, so I'll circle it. The 99 factors into 9 and 11. And then 9 factors into a 3 and a 3. So I will circle all the primes here. And once I do that, I will list them underneath the 154. So here we go. So I have a 2 times 3 times 3 times 11. Okay, to get the GCF, I just look to see which factors are common to both numbers. So in this case, I see it 2's over here, and those are common, so I'm going to take the 2 times. Okay, what's the next one? There's a 7 here on the top, but no 7 on the bottom, so I cannot take it. There's an 11. They both have an 11, so I'm going to circle the 11, and then the 2 3's I can't take because they are not common to both. So really it's just 2 times 11, which is 22, and 22 is the GCF, the greatest common factor of both of those numbers up top. Okay, moving on to the lowest common multiple, and you might recall from previous years that the lowest common multiple is the smallest multiple that all the numbers in the set share. For smaller numbers, you can determine the LCM through inspection. However, for larger numbers, we have to use the method of prime factorization. And you'll just recall that a multiple is a product of a given whole number and an integral value. Integral value means a number 1, 2, 3, 4. So for example, 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21, and so on. So these numbers here are the multiples of 7. Okay, let's do the first example down here. Let me blow it up a little bit. State the lowest common multiple for each set of the whole numbers by inspection, which means in your head doing it mentally. So 5 and 7, well, the multiples of 5 are 5, 10, 15, 20, 25, 30, 35. The multiples of 7, well, they're listed for us up here, and I can tell that the lowest one, the first one that they both share, is 35. So the answer for this one is 35. Okay, the lowest common multiple of 10, 15, and 20, well, let me see, I might be able to do this one. So 10, 20, 30, 40, 50, that is for 10. Let's look at 15. So I have 15, 30, 45, 60, and for 20 I will get 20, 40, 60, 80. Okay, let me see, are any of these common? Well, I think I have to do the 10 and one more to all the way to 60, and then I see that 60 is my lowest common multiple that they all share. I think that is correct. Yep. So 60 would be the answer. Now, you can tell this. I mean, these numbers are pretty small, 10, 15, and 20, and when the numbers get really large, this will take 15, 20 minutes just determining the lowest common multiple. So the quicker way of doing this will be the method of prime factorization. Okay, so let's get on with that. All right, example number 4. State the LCM for each set of whole numbers using prime factorization. Okay, let me zoom in here. Okay, 15 and 35. So again, I will start with a factor tree, and 15 factors into 3 and 5. So underneath here, I'm going to write 15 equals 3 times 5, and both of these are prime, so we'll circle them. Alright, 35 factors into 7 and 5, and both of these are prime, so I circle both of them, and underneath here I'm going to list them out. 35 equals 5 times 7. Okay, so the method of getting the LCM is similar to the greatest common factor. However, this time you take all the numbers, even though they might not be common to both 15 and 35, both of the numbers. So for example, I see there's a 3 over here, but no 3 on the bottom. But because it's unique, we're going to circle it anyway. And then I see a 5 over here and a 5 over here, but we're only going to take one of those 5s. And then the 7 is also unique. However, we are going to take it because we're doing the lowest common multiple this time and not the greatest common factor. So once I determine the numbers, I just write them down here. 3 times 5. I only take one of the 5s because they both share it, and then I take the 7 because it's unique. So 3 times 5 times 7 is 245. So my lowest common multiple for 15 and 35 is 245. Okay, again, I would like you folks to do B and C, and I will try and do a little bit harder one down here, D. Okay, so let me zoom in here. I will need lots of space because I have 3 numbers this time, so the lowest common multiple of 3 numbers. Again, same method. I'm going to start with doing the prime factorization for all of my numbers first. So 22 factors into 2 times 11, and then both of those are prime, so I'm going to circle them. 154, and I think I did this one in the previous example, and as I recall, I think it was 2 times 77, and then 7 times 11. 2, 7, 11, and then 198. Oh, I did that one as well. That was 2 times 99, and then 9 times 11, and then 3 times 3. Alright, 2 is a prime, 3 is a prime, 3 is a prime, and 11 is a prime. Okay, now I'm going to list them all out down here. So 22 equals 2 times 11. 154 equals 2 times 7 times 11. 198, the factors into 2 times 3 times 3 times 11. Alright, well I can clearly see they all have a 2, so I'm only going to take one of those 2's to determine the LCM. So I'll do it over here. So 2 times, okay, I see an 11 and they all have an 11, so I'm only going to take one of the 11's. Now I see a 7 over here, but no 7's on the bottom. There's a 3 here and a 3 here, and unlike the greatest common factor where we would only take the 2 and the 11, this time I have to take all the unique ones as well. So both of the 3's and the 7. So times 3 times 3 times 7. And you need to get your calculator out to determine the answer to this one. So let me get my calculator out. So 2 times 11 times 3 times 3 times 7 gives me 1,386. Okay, hopefully after doing a few of these examples, everybody's going to be comfortable with determining the greatest common factor and the lowest common multiple. The key thing is for the GCF, you only take the ones that are common. For the LCM, you take the ones that are common and all the unique ones as well. In this case, the 3's and the 7. All right. Moving on. Okay, prime factorization of a perfect square. Well, we can further use the method of prime factorization to determine if a number is a perfect square. And looking at the definition here, a perfect square is a number that can be expressed as the product of two equal factors. For example, the number 9 factors into 3 and 3, and because these are two equal factors, the number 9 is a perfect square. So example number 5, they want us to list the first 15 perfect squares. Okay, so I'm going to start with 1, because 1 times 1 gives me 1. Okay, the next one, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49. Looks like I'm going to run out of room here to get all 15 in. 8 times 8 is 64. I'm going to go up here. 9 times 9 is 81, and then 10 times 10 is 100. 11 times 11 is 121. 12 times 12 is 144. Okay, let me shift over here. Okay, what am I at here? 13 times 13, I believe, is 169. 14 times 14 is 196. And 15 times 15 is 225. Okay, so I expect everybody to remember the first 15 perfect squares, and if you remember these, many of your calculations and your questions, you'll be able to do them a lot faster. Okay, let's. But the first 15 are fairly straightforward, and most of us can remember that. But what if we get into really large numbers? How are we going to know if they are perfect squares? Well, again, the method of prime factorization is going to be help us with that. Okay, so here we go. So it says down here, example number 6, complete the prime factorization of the following perfect squares. Okay, let's do this one. 576. So 576 factors into, again, I'm not really sure. I'm going to try 4 here. 576 divided by 576 divided by 4. Yeah, that works. So 4 times 144. And then 2 times 2, 12 times 12. And these are prime, so I'll circle these, but these 12s further factor into 2 and 6, and then 2 and 3, 2 and 6, and then 2 and 3. And what I'm starting to see here is that, so to determine if 576 is a perfect square, I'm going to have to see if my factors down here at the bottom are in two equal sets. So let's do it this way. I think it's probably the easiest thing. So I'm going to draw a line here, and I'm going to take my first factor over here, and that's a 2, and put its pair over here. So 2 and 2. Okay, those are done. There, and then I'm going to take another 2 over here, and another 2. Okay, so far I have pairs on both sides. Okay, there's another 2 and another 2, so 2 and 2, and then finally a 3 and a 3. So it looks like this is a perfect square because I have equal pairs of factors on each side here. So let me see, to determine what the actual what the square root of 576 is. I'm just going to do 2 times 2 times 2 times 3, and I'm going to get 8 times 3, 24, 24, and 24. So I'm going to check on my calculator. 24 squared gives me 576, or the square root of 576 is 24. Okay. Now some of you are probably thinking, well, we could have earlier detected that this is a perfect square because I had a 12 and a 12 and a 2 and a 2 at this stage of factoring over here. And as I can see, those are fairly they're mirror images of each other. So there's two 2s and two 12s. And we could have just done it that way and stopped right there. We could have done it this way, do another table here. So and I could have taken just the 1 2 and then the other 2, and then instead of doing further factoring, I could have done a 12 and a 12, and then again I would get 24 and 24 on each side. So if you start to see this sort of symmetry starting to happen, then you know you have a perfect square. Okay, let's do the next one over here. 1296. Okay, so first I'm going to do the factoring, and again I think I'm going to start with a 4 because I know 96 divides into 4. Okay, so 1296 divided by 4 is 324. This one is 2 and a 2, and there's my first matching pair there. They're mirror images of each other. Okay, but I got to keep going further down with my 324. So 324, divide that. I'm going to try 8 this time. No, 8 doesn't work, so 324. I'm going to try 4, and that works. So 4 and 81 give me a multiplied to 324. Well, the 4 is 2 and a 2, and there's another matching pair, and the 81 splits into 9 and 9, and there's another matching pair. And if I do my sort of symmetry here, I have a 2 and a 2, another 2 and a 2, and then a 9 and a 9. I could have kept going and done this as 3 and a 3 down here, but that's unnecessary because I can see the 9s are a pair. Okay, so what is then the square root of 1296? Well, 2 times 2 is 4. 4 times 9 is 36. 36. So 36 times 36 gives us 1296. Now, if I was lucky, I could have started my factoring right from the top as 36 times 36, and I would have been okay. Well, I'm done. There's my perfect square because it has two equal factors. Okay, moving on to example number 7. It says in each case use prime factorization to determine if the number is a perfect square. Well, if the number is a perfect square, state the square root of the number. Okay, I'm going to let you folks do A and B, and I'm going to jump onto C over here. Alright, looks like a very big number, but I see right away that I can cut it down into 100 and 441. Well, the 100 factors into a 10 and a 10, and there's my first matching pair. So I'm going to leave it at that and move on to the 441. and 41. And I'm not really sure, but I think a 3 will work. So 441 divided by 3 gives me 147. And then probably another 3 divided by 3. 3 and 49. Oh, there's another pair that I see right here between the 3's, so I'll take those there. And then the 49, I memorized these ones, factors into 7 and a 7, and there's another pair there. So 7 and 7. I could have kept going with the tens over here, but that's unnecessary because they're already found a pair there. So let me, if I do it this way, there's 10 and a 10, a 3 and a 3, and a 7 and a 7, and that's obviously a perfect square because I'm getting mirror images of the factors. So what is the square root of 44,100? Well, 10 times 3 times 7 gives me 210. So 210 is the square root of 44,100. The square root is 210, and I'm not sure why my pen exploded like that. Okay. Or you can write 200. Oops. Let me try blue here. 210 squared gives you 44,100. Okay. We can do the same strategy for finding the perfect cubes, and if you recall, a perfect cube is a number that can be expressed as a product of 3 equal factors. So the factors of a perfect cube will occur 3 times. So unlike the perfect squares where we're looking for pairs, this time we're looking for triplets. If the prime factorization of a number does not result in factors in sets of 3's, then the number is not a perfect cube. So let's mentally do the first 10 perfect. Well, that should say cubes. Okay, I'm going to make my pen a little bit wider. Okay. So the first one, again, I'm going to start with 1 because 1 times 1 times 1 is 1. So that works. So 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. 6 times 6 times 6 is 216. 7 cubed is 343. 8 cubed is 512. 9 cubed is 729. And 10 cubed is 1,000. Alright, so let's see if we can determine if the following numbers are perfect cubes using prime factorization. And again, I encourage everybody to remember the first 10 perfect cubes because it will make your life easier on exams and tests and when you're doing homework. You can do it much quicker. Okay, so this is a really big number here, and I cannot do that in my head. So I need to do the prime factorization method. Okay. So starting off, I'm going to do a factor tree again. But this time I'm looking for triplets or sets of 3 equal factors. So I'm going to start with a 2 because I'm not really sure what else will go into 6,912. So 6,912 divided by 2 gives me 3,456. And I'm going to try dividing that by 3. And that gives me 1,502, and I'm going to divide that by 2, and that gives me 576. And keep going down, divide that by a 3. That works. 3 times 190, 192. Okay, I'm running out of space here. 192 divided by 2 gives me 96. 96 divided by 3 gives me 32. Oops, definitely running out of room here. I'm going to shrink it a little bit. And 32 factors into 2 and 16, and 16 factors into 2 and 8. And I'm going to have to do the 8 over here. The 8 factors into a 2 and a 4, and the 4 factors into a 2 and a 2. So wow, we have a lot of factors here, but I'm looking for sets of 3. Once I have a set of 3, we can do it this way now. I will do 2 lines like this, and I'll start with my 2. So there's a 2 here, a 2 here, and a 2 here. Okay, there's a 3 here, 3 here, and a 3 here. So far, pretty good here. Okay, there's a 2 here, a 2 here, and a 2 here. However, I'm only left with 2 2's, 2 and a 2. So I don't think this is a perfect cube, because I'm missing my third 2 in the bottom here. Let me double check this. Yeah, so this number 6,912 is not a perfect cube. I would need I'm missing a 2 over here. If I had a 2, then it would have been. Okay. Let's do the last one together over here, and this will be the last question, last example of today's lesson. So we have a really big number, 970,299. Okay, I'm gonna start by doing the prime factorization for it. So where do I begin here? So let me try 9, and 9, my calculator, 9 times 107,811. Alright, and that is going to factor into 3 and 35,937. I have a feeling I'm going to run out of room again. But let me do this 9 over here into a 3 and a 3, and there's my first triplet I see right there. Okay, so I'm going to box those, because that's my mirror image there, my triplet there. All right, but I got this big mess over here that I have a feeling I'm going to run out of room here. So keep going down the line here and divide that by 3. It gives me 11,979, and divide that by 3. It gives me 3,993, and divide that by 3 gives me 1,331. Okay, there's another triplet right there. So far so good. I'm gonna take this 1,331 and move it up here, because I ran out of space down there. Okay, so divide that by 3. No, that's not gonna work. So 3,1 divided by. Okay, this factors into 11 and 121, and then 121 factors into 11 times 11. So there's my third. There's another triplet there. So and those are all primes. So this number is indeed a perfect cube. So let me double check. I will do my table here, three-way table this time, because I'm looking for triplets. So I have a 3, 3, 3, those three up there, 3, 3, 3, and 11, 11, and 11, and 3 times 3 times 11 gives me 99. And if I go 99 cubed, or 99 times 99 times 99, I indeed get this number over here. In other words, the cube root of 900, let me write that out, need some space over here, so the cube root and a cube root, I need a little 3 here, the cube root of 970,299 will give me 99. Okay, that is our lesson. Thank you.